So what I want to do today is just quickly go over some of the topics. If there are other things you want to study for this course, by all means I'm open to them. These are ones that are either in the book or that I have worked on extensively and have good literature sources. By all means, please speak up as I'm lecturing about things you want to know more details about. This is meant to just give you a quick introduction as to what the various topics are. So if you're taking this as a 300 level class, I expect you to do at least 3 of the topics on the list. If you're doing it as a 400 level, I expect you to do at least 4 of the topics on the list. You can choose how many topics you want. You can choose, do you want to get into a lot of detail on one and maybe less detail on the other? Lots of flexibility. So the first one, and I'll assume you'll tell me when I'm too far out of the range. Okay.
Cut out the zeta.
We don't want to cut out any of the zeta function. Okay. So the Riemann zeta function is undoubtedly one of the most important functions in mathematical physics. And so it's defined as zeta of s is the sum, n goes from 1 to infinity, of 1 over n to the s. And this makes sense at least so long as the real part of s is greater than 1. And what's miraculous is it turns out this is the same as the product over primes of 1 minus 1 over p to the s inverse, where p ranges over the primes. The reason for this equivalence is basically unique factorization. Every integer can be written uniquely as a product of primes. And this is true, as I said, so long as the real part of s is greater than 1. So the question is, why do we care about this? Well, if you study number theory at all, the primes are the building blocks of number theory. So clearly you want to know as many things as you can about the primes as possible. What we're really doing is we're trying to build a function out of the primes. Now, if you've done any work, you know how difficult it is to say anything about the primes. Unless you, of course, you read general math in the archive section. Oh, this is being recorded for posterity. Where there are lots of wonderful, wonderful proofs of, great results in 2 or 3 pages. So the reason this is so useful is that there's basically a transfer property going on. So we transfer knowledge of integers to primes. So as anyone who has taken a class with me knows, the integers are not that mysterious. You give me the 15th integer, I know exactly where the next integer is with no error. It's very easy. The integers are quite well understood. And the idea is by understanding this function here, we can use that to deduce things about the prime numbers. So the first standard example is, if you take the limit as s tends to 1 of zeta of s, what do you get from this sum?
Blows up.
It blows up. And so this is basically just the harmonic sum, the sum of 1 over n, so it's plus infinity. This implies there must be infinitely many primes. If there weren't, then this product would be finite, as s tends to 1. So this implies pi of x goes to infinity, where this is the number of primes at most x. You can actually do a lot more. You can use this to deduce some estimates about how rapidly the primes diverge to infinity. And in fact, you get that the sum of the reciprocals of the primes diverge. What else can you do? You could look at zeta of 2. There are many different ways to calculate the sum of 1 over n squared. Some of my favorite ones involve Fourier analysis, which we'll talk about later. The calculation you get is this is pi squared over 6. And this is an irrational number. This also implies that there are infinitely many primes. Why? If there were only finitely many primes, if I just take s equals 2, I get a rational number. So this also implies that there are infinitely many primes. Now what's particularly nice about this is this method at first does not seem to say anything about how rapidly pi of x grows. Here I can get the sum of the reciprocals diverges. Can you somehow extract from this information about how quickly pi of x grows? At first it seems like the answer would be no, because this is just, well, if this were a rational number, if this is an irrational number, if there were only finitely many primes, this would be rational. There are ways to talk about how irrational a number is. And that's actually one of the topics later, on continued fractions. And so I know Carlos, over the summer, was playing a little bit with an idea I had a couple of years ago about trying to extract a really bad growth rate for pi of x from something like this. Alright, so this is just 2 values of the zeta function, basically zeta of 1 and zeta of 2. Already they're giving us a lot of information about the primes. Now, the great insight Riemann had is don't just look at this as a function of a real variable, look at it as a function of a complex variable. Now if you take complex analysis, what is the first thing that should come to your mind when you see a complex function? One of the first things. So actually I think, Jake, you're the only one who's taken complex analysis, so I'll put you on the spot.
Whether it's poles or
Where is its poles, where is its zeros? And so it's not that hard to show that the zeta function has a pole at s equals 1, that it blows up. A very good thing to do in complex analysis is to look at the logarithmic derivative. And so d by ds of log of zeta of s is just zeta prime of s over zeta of s. And then if I do contour integrals of this, so I integrate zeta prime of s over zeta of s, and then I'll put in some test function here. The actual test function you use, we'll discuss in greater detail later. The main result in complex analysis is that when you have integrals like this over some region, the way you evaluate this integral is you complete the contour, you shift the contour, and what comes out is a sum over the zeros and the poles of the function. And we can actually use this to actually get a function that counts how many primes there are. And this is how we prove, or at least one of the two ways we prove the prime number theorem. The number of primes at most x is roughly x over log x. So one great topic is to actually see the prime number theorem, how we would prove it. Now, of course, this is not the only question you can ask. You can then ask more refined questions about the distribution of the zeros of this function. And so how they fall will have a great impact on the number of primes up to a given level. It'll have lots of applications to other things in number theory. You can also look at more than just the Riemann zeta function. So the Riemann zeta function is the first of what we'll call an L function. And the idea is L functions encode interesting arithmetic. And so depending on what problem you're looking at, we can have a different L function, and the analysis of that L function can tell us something important. So one of the big topics people look at is elliptic curves. So an elliptic curve, say E, is y squared is x cubed plus ax plus b. Say a and b are integers. And you can look at all pairs of x and y that are rational that solve this. And so we'll call that the Mordell A group. And we'll denote it E of q. It's the set of all x, y solving the above. And so, of course, by naming it the Mordell A group, I'm kind of cluing you in as to one of the nice properties this set of solutions has. Namely, it's a group. There's a way to define a group law on these points. And the most natural thing you can then ask is, okay, well, what is the structure of this group? It turns out that this is a finitely generated abelian group. You can write it as some number of copies of z plus a torsion part. And so Rg is called the geometric rank. Okay, why is this so interesting? Well, it turns out elliptic curves can be used for a lot of things. If you're a number theorist and you're filling out an application for federal funding, you can say, and my work is related to elliptic curves which occur in cryptography. So, one wonderful application of elliptic curves these days is for making various crypto systems. They're also just mathematically interesting. They're examples of cuspidal new forms. There's a very rich theory of quantities that generalize the Riemann zeta function. I'm not mentioning all of them by any stretch of the imagination. It turns out you can build an L function attached to this elliptic curve. And you define LES to be basically the sum, and it goes from 1 to infinity, of an over n to the s, where AP is basically p minus the number of solutions to y squared is congruent to x cubed plus ax plus b mod p. So what we're doing is we're taking local information. We're counting the number of solutions modulo a prime. I'm not quite telling you now how you build this up at the things that aren't primes. There's a way to do that. It turns out this also has an Euler product. Both of these turn out to have an analytic continuation, so you can make them well-defined not just for a real part of S sufficiently large, but for all values of S. And in fact, it was this continuation and ideas along these lines that Wiles had to do to prove Fermat's last theorem. And so the amazing conjecture due to Birch and Swinnerton and Dyer is that if you look at this L function, it has a certain vanishing at the point s equals 1/2. It's conjectured that that vanishing, known as the analytic length, is actually equal to this number over here. That basically the size of the group of rational solutions is controlled by the number of zeros that this L function has. This is just one of many situations where zeros of L functions tell you things about a problem you want to understand. I'll just mention one last family of L functions that's worth studying. So, probably should have done this a little bit before the elliptic curves. There's the Dirichlet L functions. And so Dirichlet L functions, these are the form Ls chi is the sum, and goes from 1 to infinity, of chi of n over n to the s, where chi is a character on z mod mz for some m. And then you can extend this by periodicity to all the integers. So this is going to be a number of complex value 1, absolute value 1, complex number. And you can build an L function like this. This will also have an Euler product. This will also have an analytic continuation. And the reason we care about these ones is, let's say you have the following. Question. Are there infinitely many primes congruent to A mod B? Or let's say A mod M. So if I give you any A and M, must there be infinitely many primes congruent to A mod M? No. Clearly, if A and M are not relatively prime, there's a problem. Alright, so let's assume we're not stupid. We assume A and M equal 1. Let's ask an easier question. Is there one prime congruent to A mod M? Just, is there even one prime? To some extent, either the easiest or the only way to really solve this is to actually use these L functions, and to use this entire family of L functions to analyze this question. And it's a really nice proof. This leads to Dirichet's theorem for primes in arithmetic progression. The full proof uses some algebraic number theory about class numbers. It's a wonderful, wonderful result. And what I particularly like about this, and this leads in beautifully to the circle method, is it is a terrific example of overkill. How do we prove that there is at least one prime congruent to A mod M? Well, we let pi of x be the number of primes at most x. In what should be obvious notation, pi am of x will be the number of primes congruent to A mod M that are at most x. We prove that this is equal to pi of x over phi of phi of m. So this is the number of numbers relatively prime to m, plus small. So since this tends to infinity, there must be at least one prime. This is enormous overkill. We prove the existence of one by showing that they all occur with the right frequency. Another great thing that you can read about is biases between the different congruence classes. To first order, all the different congruence classes have the same number of primes. What if you subtract the main term and then look at what's left over? How are the fluctuations behaving? This is known as Chebyshev's bias. There's a lot of wonderful papers on this subject. It is crucially dependent on the distribution of zeros of these L functions. And so if you want to actually look at a wonderful topic, that's a wonderful thing to read up to. Alright, so I'm going to ask you to actually hit stop after each topic, just so the files don't get too long.